Welcome back to an introduction to real analysis, where we continue going section by section. We now begin chapter 3, continuous functions, with section 1, limits of functions. We begin with cluster points. So before we get to defining continuity of functions, we're going to visit a more general notion of a limit than what a sequence does back in chapter 2. So given a function f, which maps the set S into the real numbers, we want to see how f of x behaves as x tends toward a certain point, and we're going to have to formalize that more. So first, we're going to return to a concept that we looked at in an earlier exercise. If we move within the set S, we can only approach points that have elements of S near that point. That's what we mean by approach. So if a point is bounded away from S, we can't approach that point using elements of S. That brings us to this definition, cluster point. Suppose S is a subset of the reals. A number x is called a cluster point of the set if, for every epsilon, which is positive, the set, and now this is the interval x minus epsilon to x plus epsilon, in other words, all points whose distance to x is less than epsilon, intersect s minus x, is non-empty, meaning you have to have points that are within epsilon of x, that's being in that first interval, are in the set S, but are not the point x. So points close to x, not equal to x. And here it is formalized with symbolic operators. For every positive epsilon, there is a y in S, so that the distance from y to x is less than epsilon, but is not 0. So in other words, y is not equal to x. So what can we say about this definition, cluster point? So a cluster point of S is not itself required to be in S. The number x in this definition was not forced to be in the set S. So here are some examples. We're not going to go through proving it, just some discussion. Suppose you have a single element set. There are no cluster points. Okay, X is not a cluster point because to approach X itself, you would have to use points in the set other than X, and there are no points in the set other than X. However, any point that isn't in this set, any point that isn't X, is in fact bounded away from the set, and therefore the only option of a point in the set, X, is not within epsilon of whatever point you picked, provided you pick epsilon small enough. The natural numbers also has no cluster points. Any particular natural number cannot be approached using other natural numbers. However, if you look at the set 1 over n, so 1, 1/2, 1/3, 1/4, etc., there is a single cluster point, and that is 0. You can get very close to 0 using elements of this set, and those elements are not actually equal to 0. But that is in fact the only cluster point. Also, any open interval from A to B, the set of cluster points is the entire interval from A to B, including points in the set itself that you started with. So it's fairly clear that you can approach A using elements of the open interval from A to B, and you can approach B using elements of the open interval from A to B. But you can also approach any other point. So for the sake of argument, suppose you're looking at the open interval from 0 to 1. You can approach 0 using the points 1 over n. You can approach 1 using the points 1 minus 1 over n. But you can also approach 1/2 by using things like 0.4, 0.49, 0.499, etc. Those are getting very, very close to 1/2 without ever actually being equal to it. So the cluster points of an open interval is the associated closed interval. And finally, the cluster points of the rationals are every real number. Now we can move on to proposition 3.1.2. Suppose you have a subset of the reals, then a particular x is a cluster point of S if and only if there is a sequence so that every element of the sequence belongs to the set S, no element of the sequence equals x, and the sequence converges to x. So let's prove that equivalence. Proving this proposition, suppose you begin with a cluster point of the set S. Let's remind ourselves what that definition is. We are assuming this to be true right now. So for every n equals 1, 2, 3, and so forth, epsilon 1 over n is a positive number, but we're assuming the red definition is true. Specifically, for every epsilon, there is a point in the set where this chain of inequalities holds. So there is a y in the set where this chain of inequalities holds. Let's call that point x sub n. We now have all three of these conditions satisfied. The point was in the set. It isn't equal to x because this absolute value was not 0. And by applying a squeeze law argument, we see that the x sub n's will in fact be converging to x. Now let's take a look at the converse. Suppose that we have such a sequence. Now we assume that the blue square has happened, that we have a sequence xn belonging to s, never equal to x, but converging to x. Now, by assumption, because the sequence is converging to x and are not equal, for every epsilon, there is a cutoff point in the sequence past which every term of this sequence satisfies this inequality. But because they are not equal to x also satisfies this inequality. And since that holds for every epsilon, past a certain point in the sequence, there are terms in the sequence that make it true. In other words, there are elements in S that make that statement true. Now we can define what limits of functions are. So suppose you have a function defined on the set S, and C is a cluster point of S. We can define the limit of f of x as x approaches that cluster point. Now, it's actually irrelevant for the definition whether f of c itself exists or not. Even if the function is defined, the actual value there is also not relevant. So now let's define it. If f is a function mapping a set S into the reals, let C be a cluster point of that set. Suppose there exists a real number L, and for every positive epsilon, there is a positive delta, so that whenever x is in the set S but not actually equal to C, and its distance to C is less than delta, you automatically have the distance of f of x to L being less than epsilon. Then we say f of x converges to L as x goes to C, or the limit of f of x as x goes to C is L. Notated in either of these ways, this one on the right is more common and generally easier to read. The limit as x approaches C of f of x equals L. Here it is in terms of its formal symbolic operators. For any positive epsilon, there is a positive delta, such that for any element of S, if x is within delta of C but not equal to it, then f of x is within epsilon of L. So let's start working with this new definition. Suppose f is defined on a set and C is a cluster point, then if the limit as x approaches C of f of x equals L1, and the limit as x approaches C of f of x equals L2, then L1 equals L2. So let's prove this. Here's our definition of these limits existing. Let epsilon be positive, so there is a delta 1 which will apply to this limit. As long as x is within delta 1 of C, then f of x is within epsilon of L1. But if x is within delta 2 of C, then f of x is within epsilon of L2, because this limit holds. Picking the smaller of the two, if x is within that distance of C, then both conditions hold. Meaning the distance between L2 to L1 is simply equal to this. This is just playing around with adding and subtracting the same quantity. Triangle inequality split this up. Both of these were less than epsilon over 2, overall less than epsilon. The only way L2 minus L1 can always be less than epsilon for an arbitrary epsilon is when they are the same. Okay, here's another example. Let f of x be ax plus b for every real number. Then for every real number, we have that the limit as x approaches C of f of x is a times c plus b, which is in fact the same thing as f of c. Suppose epsilon is positive, set delta to be this particular positive number, epsilon over the absolute value of a. Now, if a is 0, you can't do that, but in that case, just pick any positive number you want, it won't really matter. If a is equal to 0, note that this function is actually constant. F of x is simply the constant b. Now, for any x, so that the distance from x to C is positive, so I didn't actually pick C, but the distance is less than whatever delta we defined. F of x is ax plus b. AC plus B is right here. This B minus B will cancel out. You get AX minus AC, which you can factor out this A, but now X minus C is less than delta. If A isn't 0 and we picked this for our delta, we end up with exactly epsilon. If A was 0, then A is 0 right here, and we have 0, which is already less than epsilon. That's why delta didn't actually matter for that argument. Okay, let's take a look at 3.1.5, the way it actually appears in the book. Let f of x be x squared. Then, for every c in the reals, we have that the limit as x approaches c of f of x is c squared, in other words, f of c. So pick an arbitrary epsilon. Okay, because the definition begins with for all epsilon which are positive, our proof must begin with let epsilon be positive. Then there exists a delta, so you simply have to pick it. And we're going to pick delta to be whichever of these two quantities is smaller, 1 or epsilon over 2 times absolute value of c plus 1. Then take an x which isn't equal to c, which is going to guarantee that the absolute value of x minus c is not 0. However, also assume that the absolute value of x minus c is less than delta. Now we're going to apply the reverse triangle inequality, one of the few times we really do in this course. The absolute value of x minus the absolute value of c is less than or equal to the absolute value of x minus c is less than delta, because remember we assumed that the absolute value of x minus c is less than delta, and delta was whichever of these two things is smaller, so delta is definitely less than or perhaps equal to 1. Now if we add 2c to both sides, we end up with this inequality, right? Adding 2c here changes the minus to a plus, and we simply added 2 absolute value of c to 1. So we had this choice of delta. We began by assuming this, and we have derived this inequality right here. So now bring in the fact that f of x equals x squared. So let's take a look at f of x minus c squared. We get x squared minus c squared, which factors as this. But now x minus c is less than delta, and the absolute value of x plus c is less than or equal to the absolute value of x plus the absolute value of c, the standard triangle inequality. Now we're going to use this inequality we derived earlier. This is less than or equal to 2 times the absolute value of c plus 1 times delta, but remember that delta was actually the minimum of 1 or this seemingly arbitrary quantity. And that's where this quantity came from. Why did we pick delta the way we did, specifically for what's about to happen? 2 times the absolute value of c plus 1 times delta is definitely less than epsilon. So overall, we had that the absolute value of f of x minus c squared is less than epsilon. A next example, 3.1.6. Take a function mapping the interval from 0 to 1, including the left but not the right, as such. Okay, so f of x is just the straight line x, except at the left endpoint, we map f of 0 to equal 1. Then the limit as x approaches 0 of f of x is 0, which is not the same thing as f of 0, which was 1. So pick any positive epsilon you want, set delta to simply equal epsilon. If x is in this interval, in other words, the distance of x to 0 is less than delta, in other words, less than epsilon as well, but not 0 because I didn't pick 0 itself. Okay, so the distance from x to 0 is less than delta. Since f of x simply equals x, this itself is f of x minus 0, and this was exactly epsilon. So we have a limit of a function existing, but not equaling f of that value. In other words, the actual value of f of 0 is totally irrelevant. You can imagine moving this point up and down. The actual value I picked here would not affect any of this argument. Specifically because in the definition of limits, we do not take x equals c. So what happens at c is completely irrelevant to this definition of a limit. Now, we put a whole lot of effort in chapter 2 to prove results about limits of sequences. And that wasn't meaningless. We're now going to use those results to very quickly prove similar things for limits of functions. Okay, and what we want to do is take all of the work we've done and get a lot of free results out of it. For example, suppose S is a subset of the reals and C is a cluster point. Let F be a function mapping S to R and L be a real number. Then the limit as x approaches C of f of x is L if and only if for any sequence made up of terms from the set S which are never equal to C. If the limit of the sequence is C, then the limit of f of the sequence equals L. This takes the definition of the limit of a function being L and translates it into something about limits of sequences where we already have many results, and it's an if and only if. However, before we can use this result, we do actually have to prove it. So first, let's suppose we have this function limit. Now let's suppose you have a sequence of points that are in S, but none of them are equal to C. Assume furthermore that that sequence is converging to C. Now we need to prove that f of the sequence is converging to L. But pick an arbitrary epsilon. We assumed the limit of f of x as x approaches C equals L, meaning for any positive epsilon, like we already picked, there is a delta, so that if x is in S, not equal to C, but pretty close to C, then f of x is epsilon close to L. But since xn is converging to C, this delta existing means past a certain cutoff point, this distance must be less than delta. Xn is converging to C, so for any positive number I put here, this would eventually hold. We're just putting delta there instead of epsilon. Now, since xn minus C is less than delta, and remember, in our sequence, all of the points were in S, I now have points in S less than delta away from C. That guarantees f of them is less than epsilon away from L, because this was the limit we assumed here. In other words, f of xn is approaching L. For any positive epsilon, there is a cutoff point past which f of xn minus L is less than epsilon. That's the very definition that the sequence f of xn converges to L. So we've proved half of this lemma. Which does mean we now have to prove the other direction of this proof. We're going to do it by assuming that the limit as x approaches C of f of x is not L, and deriving that this claim does not hold. Now, by saying the limit isn't L, that could mean two things. Maybe the limit exists and is something else, or maybe the limit doesn't even exist. But really all we have to do is negate the entire definition that the limit as x approaches C of f of x is equal to L. If it's not L, then this definition is simply negated. So after working through a negated universal becomes existential, negated existential becomes universal, universal becomes existential. How do you negate a conditional statement? This hypothesis must be true, but this conclusion is false. We get there exists an epsilon, so that for any delta, there exists an x which is an S, so that two things hold. This hypothesis is true, but this conclusion is false. Now if we simply pick delta to equal 1 over n, so any delta we pick, this holds. So let delta be 1 over n. There exists an x, we will call it x sub n. Because I can put a 1 over n here, and this is x sub n, we will squeeze law see that xn is approaching C, but f of xn is a fixed epsilon. This is not changing. F of xn is a fixed distance away from L. It is bounded away from L, and therefore not converging to L. So the first half was, if this assumption holds, then this conclusion holds. And now we've shown if this assumption does not hold, this conclusion also does not hold. So we've shown our if and only if. Now a nice explicit example. The limit as x approaches 0 of the sine of 1 over x doesn't exist, but if you multiply it by x, the limit as the x approaches 0 of x times the sine of 1 over x is 0. Note in both cases, x equals 0 cannot be plugged into the function, but this limit could very well exist or not. So here's a picture of the sine of 1 over x. It does strange things near 0. As x gets closer and closer to 0, 1 over x is going to plus or minus infinity faster and faster and faster, forcing the sine curve to oscillate through its periods faster and faster and faster. So as x shrinks down towards 0, this blows up to infinity, which means the sine curve is just going up and down and up and down and up and down and up and down crazy. But if you multiply that output by x, you get this picture, and we claim this does have a limit as x approaches 0. Pictures aside, let's get to proving. So for the first claim, let's take a specific sequence of x's, 1 over pi over 2 plus an integer multiple times pi. So This pi over 2 is fixed. As n goes to infinity, this goes to infinity, but we have 1 over it, so xn is definitely converging to 0. But 1 over xn is just this quantity, and the sign of pi over 2 plus n times pi is either plus or minus 1. It's oscillating back and forth, which is not converging to anything. So xn is converging to 0. F of xn is not converging to anything. This limit cannot possibly exist. For the second claim, now we can simply take any sequence xn converging to 0, but none of them equal to 0 because we're not going to plug that in. But now by the squeeze law, this sign, while it's doing crazy things, if I multiply it by x times that sign is in between plus or minus 1 times x. That gets squeezed down to 0 as x goes to 0. So xn times the sign of 1 over xn is forced to 0 by the squeeze law for any sequence xn converging to 0, no term of which is equal to 0. So by the previous proposition, the limit of x times sine of 1 over x as x approaches 0 must also be 0. One thing that's important, in that previous lemma, there was a phrase for every sequence, and that's important to really keep at the forefront. If you took the sequence xn 1 over pi n instead of 1 over pi over 2 plus pi n, then you would just get the constant sequence 0 being spit out. In that case, you would think maybe the function does have a limit and the limit is 0. But just because one particular sequence in the domain converging to 0 had a corresponding sequence in the range converging to something doesn't mean anything. It would have to be for every sequence converging to 0 in the domain. That's why in the previous argument, we found one specific sequence in the domain converging to 0, where the associated sequence in the range was not converging to anything. So with lemma 3.1.7, we can start deriving properties of limits of functions by translating all of them to limits of sequences where we already have results. So we're going to give a few important examples. Corollary 3.1.9. Suppose S is a subset of the reals, C is a cluster point, F and G are both functions with domain S. The limit as x approaches C of f of x is L1, and the limit as x approaches C of g of x is L2. Also, f of x is always less than or equal to g of x. Well then, L1 is less than or equal to L2. Proving. Let's remember lemma 3.1.7, which is going to be important. Suppose xn is a sequence converging to C, all drawn elements of S, but none of them equal to C. So, because xn is converging to C, and we did assume in corollary 3.19 as part of our givens that these limits exist, it follows that f of xn must converge to L1, and similarly g of xn must converge to L2. Now dial all the way back to chapter 2. If you have two different sequences converging where term by term you can express a non-strict inequality, then you get the same non-strict inequality in the limits. So since f of xn is always less than or equal to g of xn, that's one of our givens up at the top in corollary 3.1.9, we are assuming that f of x is always less than or equal to g of x. So this sequence term by term is less than or equal to this one. They are both converging to something. So this result tells us we get the same inequality in the limits. So this is a nice little example of, we already proved this for sequences. We can now get basically the same result for free with limits of functions. There are a lot more examples of such claims we can make, where limits of functions can be sort of translated over from limits of sequences, and we don't have to do a whole lot of work to derive these new results. It's honestly the reason we started with limits of sequences in chapter 2. So here we're going to state a whole bunch of them, and we're not actually going to prove them. Many of them are left as exercises. Others are proved so similarly to the ones that are exercises that it's not really worth even assigning them. Okay, so always what you're going to do is combine lemma 3.1.7, which says instead of talking about limits of functions, just do something about limits of sequences, and then look for a similar result back in chapter 2. So we can say, if S is a subset of the reals and C is a cluster point and F has domain S, and the limit as x approaches C of f of x is L, if A and B are two numbers so that f of x is always between A and B, well then that limit must also be between A and B. Note you can't prove this with strict inequalities. If a was strictly less than f of x was strictly less than b, you wouldn't be able to claim a less than L less than b. You would have to have the possibility of equality here. You can also prove, again, the hypothesis is going to be very much the same in many of these. S is a subset of the reals, C is a cluster point of that set. Now we have a whole bunch of functions whose domain is S. Also, let's assume that h of x and f of x have the same limit as x approaches C. And you also assume for all x other than C itself, g of x is squeezed in between f of x and h of x. Well, f of x is converging to L, h of x is converging to L, g of x is squeezed in between, therefore g of x is also converging to L. Formally, this does need to be proved. It's a new result, but it's basically the squeeze law for sequences in combination with lemma 3.1.7. Another corollary, okay, suppose you have two functions, f and g, both mapping S to the reals. S is a subset of the reals, C is a cluster point of that set. F of x is converging to L1, g of x is converging to L2. Then all of the following hold. F plus g is converging to L1 plus L2, f minus g is converging to L1 minus L2, the product and the quotient, as long as you are not ever attempting to divide by 0, which is what that giant parenthetical term is expressing. And again, this is really a result we already have for sequences, so you just need to translate it over. More corollaries. Let S be a subset of the real numbers, C is a cluster point of that set, F maps S into the reals, and f of x is converging to L as x approaches C. Well then, the limit of the absolute value of f of x must be the absolute value of L. Don't try to run this in the converse. Okay, a new definition. Suppose f maps the set S to the reals and A is a subset of S. Then this notation is called the restricted function. F restricted to the set A has domain A, and it's defined as f of x, but only for x's belonging to the set A. So it's the same function, you have just taken away part of the domain. You call this the restriction of f to A. Now the restricted function f is just exactly what we were doing, but throw away part of the domain. Now, because the definition of the limit as x approaches C of f of x depends on the values of x nearby but not at x equals C, we'll show that the limits of restricted functions are equal to limits of the original function provided that limit exists, but the converse direction isn't as obvious as you'd think. Okay, a restricted function might have a limit, whereas the unrestricted function doesn't. But we will show one special case where of this restrictions works like we would think. So prop 3.1.15. So we're going to take a function mapping a set S to R. We're taking a subset of SA on which we're going to have our restricted function. Assume there is a positive alpha so this is everything from A except for where we're going to take our limit, intersected things pretty close to C. So this is an interval around C. So altogether, this left-hand side is everything in an interval around C that belongs to A and not equal to C. Assume that that is the same thing as everything within an interval around C that is in S but not equal to C. In other words, if you are within the interval from C minus alpha to C plus alpha, and you are not considering the point S, then the set A and the set S coincide. Okay, so if you are sufficiently close to C, A and S are indistinguishable. Then C is a cluster point of A if and only if it's a cluster point of S, and in this case, the two limits are the same. Okay, if one exists, then the other does and is equal. Can we, to prove in this proposition, let's recall the definition of a cluster point. Now, the first claim that C is a cluster point of A if and only if C is a cluster point of S is fairly immediate. We just have to properly understand what we have assumed, this gigantic equality. So suppose C is a cluster point of A. We now want to show it's a cluster point of S. So let epsilon be positive. Now, because C is a cluster point of A, there does exist a point in A, very close to C. However, based on this assumption, as long as you're close to C, A and S coincide, so this point that was in A is also in S. Therefore, C is a cluster point of S. Conversely, let's suppose we have a cluster point of S. You really do the same thing. Let epsilon be positive. Assume you are within this distance of C, but also within distance alpha of C, so that A and S coincide. Since there is a point of S within epsilon star of C, this is also within alpha of C, and therefore it's within A, and therefore there's a point in A within epsilon of C. There's not a whole lot to say here. It's more confusing to say it than to just look at it. Okay, so C is also a cluster point of A. So the first claim established. Let's move on to the second claim. Assume that the limit as x approaches C of f of x equals L. Now we're going to use this sequence approach. Let xn be a sequence approaching C, never equal to C, and let's assume everything is in A, because we want to show this restricted function has limit L as well. Alpha is positive. We assumed this alpha existed, so past a certain index, all terms of the sequence are within alpha of C. But within alpha of C, A and S are the same set, so since these were in A, they're also in S. Now, having assumed this limit was L for the unrestricted function in domain S, I now have a function, a sequence, converging to C, and the tail of it at least consists of point in S. Therefore, those are converging to L as well, and therefore we have shown that the restricted function is also converging to L. The other way, suppose that the restricted function is converging to L. Take a sequence converging to C, where every xn is not equal to C but is in S. We want to show that this function is also converging to L, the unrestricted function. Again, since alpha is positive, this sequence converging to C is eventually within alpha of C. But if you're within alpha of C and you started in S, then you are also in A. So the tail of this sequence belongs to elements of A. So I now have a tail of a sequence converging to C consisting of points in A. But we also had that the restricted function had limit L, so this tail converges to L. Therefore, for any sequence in S, xn converging to C, the tail converges to L, so the entire sequence converges to L. So we're just leaning very heavily on lemma 3.1.7 over and over and over again. Okay, the point here is if A and S are identical, very close to C, then functions having limits and restricted functions having limits are the same thing. Now, this hypothesis was that A and S are the same set as long as you are close enough to the point C. So let's consider sine of 1 over x, and let's let S be all real numbers other than 0. We already know that this limit as x approaches 0 of f of x does not exist. But if we took A to be a really peculiar set, just 1 over n pi, this collection of points, it still has 0 as a cluster point, but on the restricted function, only looking at these values in the domain, the function looks like a constant, so this restricted function does have limit 0. So this is a peculiar example where the restricted function can have a limit, but the original function doesn't, because the function has been restricted to a very weird set A. It's not an interval or something. It's specifically a collection of points designed to make it look like the function was constant. Now, that said, that's a weird way to make a restricted function and not commonly how we will do so. The notion of a one-sided limit is really more how we're going to be using restricted limits. So what is a one-sided limit? For any particular value of C, let's define two sets, A plus and A minus. These are simply elements of S that are bigger than C, or elements of S that are lesser than C. So between the two sets, if you union them, you get all points of S that aren't equal to C. So let's denote the restricted limit from AC plus. If you're only allowing x to approach C and be bigger than C, if this limit exists, you say the limit as x approaches C from above. Similarly, the restricted function on AC minus, where the domain only accounts for things less than c, if that limit exists, you call it the limit as x approaches c from below. These are one-sided limits that many of us have probably seen before in our elementary calculus courses. Now, Prop 3.1.15 does not apply to one-sided limits. Let f of x be the so-called Heaviside function. This is the function that jumps from 0 to 1 at a specific point, usually the origin. Then, the limit as x approaches 0 from above is 1. If you cut out this part of the domain to the left, the function looks like a constant. 0 is a cluster point, and if you approach from this side, you simply see 1 as a limit no matter what. But if you approach only from the left, you see 0. However, the limit overall for the unrestricted function does not exist. If you take the sequence plus or minus 1 over n, 1, negative a half, positive a third, negative a quarter, positive a fifth, etc., the value of the function along that sequence will jump back and forth between plus or minus 1. Now you have a sequence in the domain converging to 0 where the associated sequence in the range doesn't converge to anything, so the function doesn't have a limit overall. But the two one-sided limits do exist. For the restricted domains to the right of 0 and to the left of 0, you cannot achieve this oscillation. Okay, we will see a familiar Calc 1 result in just a moment. So here is that familiar result. Let S be a subset of the reals. C is a cluster point of both AC plus and AC minus. So C can be approached from above and can also be approached from below using the set S. Then C is a cluster point of S, and the limit as x approaches c for the unrestricted function f is L if and only if both one-sided limits exist and are equal to the same L. Can we prove it? Can we prove this old familiar result? We are not going to because it's an exercise. This is exercise 3.1.12. I will, however, give a little hint. The key observation to proving this is that if you look at all points in S other than C, this can be represented as a union of everything in S which is bigger than C, union with everything in S that is lesser than C. So, the two restricted limits account for this side and this side individually. Between these two sets, we do account for all possible points in S other than C itself. That's really the observation. What's important here is that this limit for the function overall has to account for all points in S other than C. If you can account for one side and then the other and you get out the same thing, you need to somehow glue those two things together. Now, whatever proof you come up with, you should always have this running picture in your head that our domain is the real numbers and can be cleanly split into a bigger than C and less than C. A sort of similar argument shouldn't work very well if your domain was more than one-dimensional. Let's go over what we did discuss here. So a cluster point is a common obstacle at first. The technical definition I wouldn't get hung up on. In fact, in different sources, these can be called cluster points or accumulation points or limit points, and the actual definition might slightly vary from book to book. The main idea is that these are points that you can get very close to using the set S. That's the key notion. Now, the more important thing from this section is what it means for a function to have a limit. And sure, the definition of cluster point was sort of baked into there because you can only take a limit at a cluster point, but try not to focus on that half of it at first. Focus on the other part, that for any epsilon, there is a delta, etc., etc. Okay, so the connection between functions having limits and sequences having limits is kind of a formalism, but it makes really convenient the work of proving results for limits of functions. You could manually reprove all of them using the definition of the limit of a function. What's a lot easier is to simply say, hey, we already did this for sequences.